student talk from Shahar Dery from the group of Dr. Elad Gross from Hebrew University, where Shahar will speak today on identifying catalytic reactions in the nanoscale. Shahar, good. Yes, the board is yours now. Good luck.
I can unmute. Okay, can you hear me well? Yeah,
Yes.
Thank you. So hi everyone, my name is Shahar Dery and I'm a PhD student at a group of Professor Elad Gross at HUJI. And this talk will focus on identifying catalytic reactions in the nanoscale. And I want to start off with the link between structure and reactivity in heterogeneous catalysis. And here I brought you an STM image of a single catalytic particle, and you can see that even in a single particle level, we have different surface sites. We have this flat surface in the center, and we have steps and the metal-metal oxide interface. And these regions, because of their different structure, can lead to dissimilar reactivity. And here lies one of the goals in heterogeneous catalysis. We want to create optimized catalysts. And the way to get there is to understand which are the highly active surface sites and which are not, which are sluggish. And of course, we need, in order to do so, we need to identify catalytic processes in the nanoscale. And for this reason, we use a cutting-edge technique termed IR nanospectroscopy. And in this method, we focus a synchron-based IR beam onto the apex of an AFM tip, an oscillating apex. And the apex or the tip acts as a nano antenna, focusing and scattering the IR light, and thus creating a local electric field right beneath its apex. Now, this allows us to extract localized IR information from a radius which is approximately 20 nanometers. That's far beyond the diffraction limit of light. And this is a great tool, really, but the problem is that we need a surface marker for surface-induced reactivity that can actually absorb in the IR range. And for this purpose, we use N-heterocyclic carbines, these molecules, and we deposit it on the surface. And in this case, we use hydroxide-functionalized NHCs. And these act as surface marker for oxidation, this transformation from an alcohol to a carboxylic acid. Now, this is our model system. Now that we understand it, the question that we wanted to ask or to first address is how do reaction conditions influence reactivity? And that means just taking our sample and exposing it to 1 atmosphere of oxygen or to 0.1% hydrogen peroxide. And these are the results or typical results. So what you see here on the left is an AFM topography image of a single catalytic particle. And the black circle here corresponds to the exact location from which we extracted this spectrum that you see. Now you can focus on this region here, which is the COH vibration, and we see a peak, a dominant one. And this tells us that we have successfully deposited our molecule on the surface. Now, during gas phase oxidation, and this is again 1 atmosphere of oxygen at 50 centigrades, we see that the region attributed to the carbonyl stretch went up. And that means that we did succeed to do this transformation to a carboxylic acid. And we saw a similar result going to liquid phase oxidation. We see, and again, this is 0.1% hydrogen peroxide. We focus on the center. And you see again that the region of the carbonyl went up. And that is again indicative of the formation of a carboxylic acid. That means that our approach is okay. We can identify reactivity in the nanoscale. But if you remember the first slide that I've shown you, we are more interested in side-dependent reactivity. What happens when you look at the edge versus the center? Now, we were able to do that by a simple analysis. So what you see here, we just took 2 measurements and we subtracted the center measurement from the edge. And for instance, for the S-deposited spectrum, you see a featureless spectrum. And that means that we have no differences between the center and the edge. And no surprises there. We did nothing. When we do gas phase oxidation, you see immediately that we have a totally different picture. And now we have two dominant peaks for the CO and the COH, and that tells us that this is side-dependent reactivity, actually. We have carboxylic acid, more carboxylic acid on the side than the center of the particle. Now, during liquid phase oxidation, we see a much noisier spectrum. We still see that the edges are more reactive, but this time we can also see probably other carbonyl species that can say that we have decomposition at the particle edges. Now, I just want to sum up this part. I've shown you that side-dependent reactivity in a single particle level actually exists, and we can visualize that under different reaction conditions. And more importantly, the conclusion is that low coordinated atoms are more abundant on the edges of the particle, in analogy to what you see here, and they are sensitive to the reaction conditions. Now, this brings me to the next topic. I've shown you side-dependent reactivity. What about side-dependent selectivity? I come from heterogeneous catalysis, and in heterogeneous catalysis, selectivity or 100% selectivity is always something that we desire. But if we talk about selectivity, we need a different surface marker. And for this reason, we use this double bond, this allele functionalized NHC, because we can isolate an intermediate. It can be partially oxidized to an alcohol that you see here, or fully oxidized to a carboxylic acid. And again, the question that we ask is, can we be selective to a specific product? Or again, seeing those differences between the edges and the center of the particle. So again, we did similar measurements, and again at ambient conditions, just to see what happens after deposition. You see, again, the AFM topography of a single catalytic particle. This is a platinum particle. And you see again, so just for color coding, the black circle here corresponds to the black spectrum that you see, and the edge is in red. And you see a similar spectrum. We see this stretch corresponds to the CC double bond and to the CH, and it's quite identical. Nothing really happens again. But when we try gas phase oxidation, and this time we went up with temperature, now it's 100 centigrades, we see a totally different picture. We see that, so if we focus on the center, we see that we lost these two peaks, these indicative peaks, and we got a peak here in the COH, which corresponds to an hydroxyl functionality on the center. And when we go to the edge, we see that we have an additional peak here at the carbonyl. And this tells us that on the edge, we're actually, again, the edge is more reactive, but this time we see selectivity, and we see that there is this carboxylic acid on the edge. And now again, for the liquid phase oxidation, which always appear to be harsher, again, we focus on the center of the particle, and we see that we have two peaks here, or maybe more, but two dominant one. And again, that means that on the center, at least, we saw this again, the formation of a carboxylic acid. And on the edge, we saw a lot of peaks. And this was, again, probably the result of some decomposition species that are occurring on the edge, or we specifically identified the NO stretch, which can tells us that we have an hydroxyl amine on the surface. So, but again, the important message to get here is that side-dependent selectivity was actually observed between the center and the edge under gas phase oxidation. And I want to, I want to sum up quickly. I know that we are out of time already. So side-dependent reactivity and selectivity was observed using our setup or our model system. And we attributed the existence of high density of low coordinated atoms at the nanoparticle edges, and they may hold the key for controlling catalytic activity or for actually synthesizing optimized catalyst. And just for the acknowledgements, so I'd like to thank my supervisor, Professor Elad Gross, for all the support, my wonderful group members, and the collaborators at the UC Berkeley, and of course the funding agencies, and for you, the audience. And I'll be happy to take any questions that you have.
Thank you, Shahar, for the very nice presentations. Are there any questions from audience? So, do you have any concern about catalyst poisoning in using your methodology, contaminating catalysts as you studied?
So coke formation or similar things are not really happening because we use really mild conditions. So one atmosphere of oxygen, you do that with a balloon and nothing really happens. Those are, so it's just a model system for heterogeneous catalysis and it works, but it's not really what we know about heterogeneous catalysis, which operates at high temperature and high pressure. So again, it's more of a model system and not really a catalysis at work.
Thank you. Any other questions? With that, let's thank the speaker again, and we move forward to our last speaker, Dr. Hannah Noah Barad from Max Planck Institute of